Hello everyone. In this video, I will go over my solution for the problem named Qpwoeirut and the city taken from today's Codeforces round. This problem is an excellent problem which teaches you how to use prefix and suffix sums in order to optimize algorithms. In this problem, we'll not be exactly using prefix and suffix sums, but we'll be using a modification of them, and we'll be understanding how we can use a modification of the general idea of prefixes and suffixes in order to speed up an algorithm. So in this problem, we are basically given Qpwoeirut city, which can be described as a row of n buildings. The ith building is hi floors high, and we are given these heights of each building. We can assume that the height of every floor in this problem is equal, and that's why the building I is taller than the building G, if and only if hi is greater than hj. Now building I is cool if it is taller than both the buildings adjacent to building I, if they exist, and that's why both of them should exist. So the buildings 1 and building n cannot be cool. Only buildings 2 to n minus 1 can be cool, and only if they satisfy the condition that they are taller than h of I minus 1 and h of I plus 1. Now Qpwoeirut needs to maximize the number of cool buildings. So to do this, he can build additional floors on top of any of the buildings and basically increase the value of hi. However, he cannot decrease the value of hi. So in short, we need to minimize the number of floors he builds, and we need to find out this minimum number of additional floors this person needs to build in order to maximize the number of cool buildings. And basically, we need to increase the values. We need to find the minimum increase in hi, total increase in hi, where we are maximizing the number of buildings which satisfy this condition. So let's look at a few examples in order to better understand the condition and how exactly we can minimize the additional number of operations required. So in the first example, where n is 3 and the buildings are 2, 1, 2, the heights are 2, 1, 2, then in this case we know that the second guy has to be a cool building, and that's why we need to increase this value to 3. So we'll perform two operations because we need to make this greater than 2, and the smallest is 3. So we perform two operations, and that's why the answer will be 2. In the next example, we see that the second and fourth buildings are already cool, and that's the maximum number of cool buildings you can have. So we will print 0 because we don't need to build any additional floors. In the third example, we need to make sure that, so from the third example onwards, we need to come up with like some logic, and not just, we can't just directly see the input and figure out what the answer is because it's a non-trivial case. So let's consider these to be the 6 buildings. Note that when there are an even number of buildings, it gets complicated. So first I'll cover the case when there are an odd number of buildings. When there are an odd number of buildings, then it's actually quite simple. The reason being, you know that the cool buildings will only be the buildings which appear at the position between 2 to n minus 1, and we want to find the maximum number of such cool buildings. That's why it's optimal in the case when n is odd to always choose these numbers 2, 4, 6, 2, 4, 2, 4, 6, 8, and so on. So when n is odd, you can see that it will always be optimal to choose the buildings which appear at even positions in the array. So that's the strategy. When n is odd, you don't have any options at all. So you need to choose the buildings at even indices and as the cool buildings. And how can you make sure that these become the cool buildings? You can make sure that these buildings are cool by basically checking whether the value is greater than the two adjacent values. So let's say you want to make a building I cool. So you know that you need to make sure that I is greater than both hi minus 1 and hi plus 1. So it has to be greater than the maximum of these two quantities. And that's why it should be greater than or equal to this plus 1. So That's why just set it equal to this plus 1, because you're just updating the values. You're increasing hi by 1, so you want to make sure that hi is equal to this, and that's why the number of operations required, number of operations will be equal to this quantity minus hi. Because if you consider an example, let's say that you're looking at the case, well, let's say that you're just looking at 3 elements, something like 1, 5 and 8 for example. Then in this case, the maximum of these two quantities will be 8. 8 plus 1 is 9, and 9 minus 5 is 4. And you can see that if you perform 4 operations, you'll increase the height of this building to 9, and that's why this this expression is correct. You can take multiple examples and make sure that you understand this very well, because this will be used everywhere repeatedly. And this is actually not the challenging part. This should be relatively straightforward to understand why this is the expression for the number of operations required in order to make building I cool. And we know that now all that is left in this problem is to figure out which are the buildings which are cool. And we know that when n is even, when n is odd, sorry, we will just take the buildings at even indices and make them cool. And that's why we can just sum up this quantity for all even indices I. So now we basically just need to consider the case when n is odd, when n is even, sorry, and let's understand exactly which buildings should we choose to make the maximum number of possible buildings cool. So before we move on to the case when n is even, I'll just show you the code for the case when n is odd so that you can understand it better, because n is even is a bit complicated. So you need to understand n is odd very well. So in the code for each test case, I take in the value of n. I use a long array because the values can be up to 10 power of 9. And I basically check for the case when n is odd. I'll initialize the value of answer to be 0, and I'll increase the answer by this quantity. This quantity is basically the value of the maximum of hi minus 1 comma hi plus 1. So the value of that plus 1 minus hi. So that's exactly what I've written in the whiteboard. So this is exactly the same thing. Note that in case you get an example where, in case you get a case when something like this happens, then the maximum of these two quantities will be 4. So 4 plus 1 minus hi will be 0, and like if it's 2, then it will actually be 2 plus 1, which is 2 plus 1, yeah, 2 plus 1, which is 3, and 3 minus 5 will become negative. So that's why you need to make sure that the quantity of hi minus 1 and hi plus 1 minus hi, so that quantity should always be greater than or equal to 0, and that's why you take the max with 0 and you use long because we need to store everything in long, and that's why we take the max with 0, which is a long, and we do this for all even indices. So for all even indices going from 2 till n minus 1, we know that n is even, so you can compute that n minus 1 will be odd. So although it's not necessary for n to be even or odd, we will just go from 2 till n minus 1, because we know that those are the only possible cool buildings, and hence we go for all even indices from 2 till n minus 1 and make sure that all of them become cool. Now let's move on to the case when n is even, which is the more interesting case. So when n is even, we need to figure out which all indices should be cool. So let's consider this example. Going back to the example from the samples itself, let's take that example and let's consider exactly how we can choose the buildings which we need to make cool. So the key idea is that there are a number of possibilities. It's not as simple as the odd case where we just choose all the even indices. In this, it's also possible that the indices can be something like 2, 4, 2, 5, 3, 5. So there are actually 3 possibilities, and you need to consider all of them, because it could be the case that for one of the possibilities the answer is more and for the other it's less, so we don't know which one would be the optimal one. And that's why let's just enumerate all of them in the beginning, and then we'll figure out a way to speed it up. So when we have the case of n 2 comma 4, in that case the answer will be 4 plus 3 my 4 plus 3, so 4 and 3, the maximum of those two quantities is 4. 4 plus 1 will give you 5, and 5 minus 1 will give you 4. So the cost will be 5 minus 1, and that's just 4, because 4 plus 1 minus 1 will give you 4. And you need to add this, obviously, to add this to the cost for the index 4. The cost for the index 4 will be the maximum of these two quantities, which is 5 plus 1, which will give you 6, minus 5, which will give you 1. So I'll directly write plus 1. So this is 5. 4 plus 1 will give you 5. So that's one option. The other option is to do 4 plus the cost for 5. The cost for index 5 is the maximum of these two, which is 5, plus 1, which is 6, minus 5, which will give you 1. So that's why it's this. And the cost for 3 and 5 will be, you need to consider the maximum of these two. So the maximum of these two ones are 5. You add 1, in which you get 6, and you subtract 4, so you get 2. 2 plus this cost we already computed as 1, so this is 3. And obviously in this case, choosing indices 3 and 5 gives you the best least number of operations, which is 3. So we print 3 in the third example. In the fourth example, in the fifth example, which is easier because you don't need any operations, you can just choose the second and the fifth one. As I explained, you can choose 2 and 5. So when you choose 2 and 5, you don't need to perform any operations. The third last and the last examples give us a glimpse into how we can generalize this for any value of n which is even. So let's directly jump to like any even n, and let's not do those examples. You can pause the video in case you didn't get the problem still and try to solve those examples. The explanation is there, I think, and you can basically try to understand it. I'll just move on to the general case when n is even. So when n is even, let's say that these are the indices, and let's say that n is some number like 8. So what are all the possibilities for the buildings which you need to make cool? The key idea is that there are one possibility, which is the simple possibility, is to choose all the even indices. Now you can modify the last even index, and make it an odd index, the next odd index, so you can make it 7. You cannot choose two adjacent indices, because if you choose two adjacent indices, you cannot make sure that one is greater than the other. So that's why you should always choose indices which are non-adjacent to each other. And like that's actually why the case when n was odd, we needed to choose all the buildings at even indices. So the reason, if you didn't get why, is because we cannot choose two adjacent indices to choose two adjacent buildings and make them both cool, because of the condition that cool buildings are greater than the buildings adjacent to them. So that's why if one number is greater than the other, you cannot make sure that the other number is also greater than the first number. And like that should be obvious, but in case you didn't get that, this is the reason for not choosing two adjacent buildings. So that's why when you consider the case when n is even, you can increase the last value to an odd value. So that's one possibility. Another possibility, so this is the normal possibility when n is even. Then this is one more possibility. Then an additional possibility is to again choose an even index, and make it odd. So you can increase 4 and make it 5. And once you make it 5, you need to make the other index. You need to make the other index as 7 only, because we know that once you make one odd, then the next one also should be odd, because like clearly we need to ensure that all the buildings are not adjacent to each other. So all the buildings have a gap of at least 2, and that's why you can't choose 5 and then 6. You should choose 7 after choosing 5. So this would be the third case. Like, so if you number these, this is the first case, this is the normal case, this is the second case, the third case, and the last case is when you increase the first number itself and you make these buildings cool. So these are all the possible buildings which you can make cool. So all possibilities for which buildings should be made cool, and we just need to basically iterate through all these possibilities. And one uh, one way to uh, improve this is to see a pattern, but you should understand why these are the only possibilities. Now let's understand exactly how we can improve the algorithm, because right now we are basically checking all of the n over 2 possibilities. Whenever n is even, there are going to be exactly n over 2 possibilities, because like when n was 6 there were 3 possibilities, when n was 8 there are 4 possibilities, and in general for any n equal to 2k there are going to be k possibilities, because you can modify the last even number and make it odd, then you can modify the second last even number and make it odd, and so on. And in general there are n by 2 even numbers, which is why there are going to be exactly n over 2 possibilities. So this is the general idea, and now I'll show you how we can optimize this idea. And we will use prefix and suffix sums in order to make this an O of 1 transition. So the prefix and suffix arrays which we'll be using are going to be defined in the following manner. Prefix of I will be sum of costs for making the buildings, making the even index buildings less than or equal to I, at places less than or equal to I, or cool. So the sum of the costs for converting all these even indexed buildings at all the positions less than or equal to I, the sum of the cost for all of that is going to be the value of prefix of I for making them cool, obviously, and suffix of I will be defined as the sum of the costs, so the exact same thing, sum of costs for making the odd indexed buildings. So this is going to be slightly different. This is going to be the cost for making the odd indexed buildings cool at places greater than or equal to I. So note that the prefix of I will be defined only for even indices I, and the suffix of I will be defined only for odd indices I, because prefix of I converts only the prefix values at positions I and less than I, and only those which appear at even indices. Suffix of I converts only those odd index buildings at positions I plus 2, I plus 4, all of them, into cool buildings by by basically applying the operation which I described. So the operation which I described for computing the cost is always going to be this. That's why it's very important you understand this operation, which basically takes the maximum of the two adjacent buildings, adds 1 to them, and subtracts the value of hi, and you take the max with 0 in the end in order to ensure that the cost will be greater than or equal to 0. So you just sum up all these costs in order to compute prefix of I and suffix of I, and I'll show you the corresponding code so that it becomes easy for you to understand exactly what is happening. So the corresponding code is going to be this. Prefix is defined for these values, suffix is defined for these values, and for all even indices you compute prefix of I, and for all odd indices going backwards you compute suffix of I. The recurrence or the method in which you compute the prefix will basically be dependent on the fact that when you're at an index I, you're going to consider the positions I minus 2. So you're going to consider I minus 2, and you're going to add the costs. So prefix of I will just be the cost for the previous I minus 2 buildings. So I minus 2 will be an even number because I is an even number, and that's why you'll add the cost for the buildings from I minus 2 plus the cost of I, and we define the cost of I as this quantity. So we'll just add the cost of I. So this entire complicated thing is actually just the cost of I, and actually I should make that change so that it becomes easier for you all to understand what exactly is happening. So these are the costs which I'm computing for all indices I going from 2 till n minus 1, and the way in which I compute these costs is this function. So I'll just cut and paste this. So cost of I is going to be this thing, and this thing is basically the maximum of the adjacent values. You add one to them because you want the current building to be greater than both the adjacent values, and you subtract the current building because you're increasing the heights of the current building, and you take the max with 0 because you want the values to be positive. So in this manner you compute the costs, and once you compute the costs, you can again make a change over here. You just need to add the costs for all the even indices. So that's the simple case for when n is odd, and when n is even, you just compute the prefix and suffix first. I'll show you how to use the prefix and suffix in a bit, but you should make sure that you understand exactly how the prefix works and how the suffix works. The suffix goes for all the odd indices. So in this case, like n is even, that's why I think it's mentioned somewhere that n is even, and that's why we will go for all the values for all the odd indices from n minus 1 till 3, and we'll compute suffix of I as suffix of I plus 2 plus cost of I, and cost of I is basically this quantity which tells you what is the cost for making building I cool. So this is the cost for making building I cool. Now let's go back to the problem and let's basically understand how we can use these two prefix and suffix sums. So the key idea for using the prefix and suffix sums is to realize that what we are essentially doing is, when we are performing these kind of these kind of operations where we change one index from even to odd, what we are basically doing is, a simple way to write this would be, for the indices 2, 4, 6 all the way up till some even index I, you will choose these as your even indices. So these are your even positions. So you choose these buildings as cool, you make them cool. Then you have a buffer, you have a possibility, you are allowed to skip I plus 1 and I plus 2 because n is even, you can afford to skip these two quantities. So when you go from 2, 4, then you can skip two indices and you can make I plus 3 even. You can make I plus 3 and cool building basically. So you can make I plus 3, I plus 5 and so on all the way up till n minus 1. So these are the odd indices. These are the odd indices. I should actually change the color, but yeah, so the even indices should be in red and the odd indices are in blue. So these are the odd positions, and you make the odd positions, basically you make the buildings at odd positions cool for the odd values of I, and before that you make all the even positions cool. And there's one additional possibility where you don't choose any even buildings in the beginning. So the last and the border case is when when the number of even positions chosen are 0. So in that case, you're starting from 3 actually, and you're choosing all the odd indices, and um, in this manner, we basically will just initialize the answer to this expression, to this cost, and then we'll iterate for all the even indices, and we'll include those many even indices in the original cost. So the way to do this is, you're basically iterating through all the even indices and you're computing prefix of I, because prefix of I will store the sum of cost for making all the even indices cool, and then you will add to that the cost for making the indices from I plus 3, and we know that since I is even, I plus 3 will be odd, and we know that all these odd indices should become cool. So all the buildings at these odd positions should become cool, and that will be the cost. So this will be the cost for making the first I buildings cool, then skipping 2 buildings and then going from I plus 3, and you take the min across this. You take the min for all possible values of I, for all I. So for all I, for all even I, you do this, and the corresponding code for this would be for all even I. You can start from 0 or you can start from 2. If you start from 0, you will note that suffix of 3 will be the initial quantity. So you can start from 0 or you can start from 2. It doesn't really matter. But you need to go till n minus 2 because, so there are two border cases essentially. Two border cases. The first border case is when, case 1 is when you don't choose any even indices. So in this case, we choose C, 5, 7, dot, dot, dot. So this implies we are choosing suffix of 3. And the second border case is when you don't choose any odd indices. So this means that you're choosing 2, 4, 6 all the way up till n minus 2. This goes up till n minus 1. Note that it goes up till n minus 2 because n is even, and that's why we can afford to skip two indices in the middle. When n was odd, we could not afford to skip these two indices. So that's the logic behind why exactly we can skip two indices in the middle. But yeah, so you should understand that first. And that's why we are able to use prefix and suffix in order to figure out which indices to skip. And coming back to the second border case, when you don't choose any odd indices, this will be computed as prefix of n because prefix of n minus 2 actually, because you are choosing the first n minus 2 even indices, and that's what happens when I becomes n minus 2. It becomes prefix of n minus 2 plus suffix of n plus 1, and suffix of n plus 1 is actually just going to be 0. So another way to write this, if you don't want to get like overflows, if you're using a normal array of size n plus 1 or size n, then you should first initialize it to the min of these two border cases, and then you can run the loop from 0 till n minus 4, I mean 2 till n minus 4, and just compute this quantity. So these are the two border cases, and then for all the other cases, we'll just iterate through all the even indices. Note that you can also iterate through the odd indices as well, but I just did this for to make sure that there's only one approach. The second approach could be you iterate through all the odd indices and do a similar pattern of choosing like prefix of the odd index plus suffix of an even index, but this method also works. So now I'll just submit this code to see that it gets accepted. So as you can see, my code got accepted, and I hope you like this problem and my solution. If you have any doubts in any part of the solution, in either of the two cases when n is odd or when n is even, or if you didn't get the prefix and the suffix part or the cost function, do leave that doubt in the comments below. And if you like this video, don't forget to give it a thumbs up. Thank you.